Hello, myself Dr. Suresh Ramsam Reddy, professor from BMS College of Engineering. I am teaching this subject since 26 years. I am going to teach you this fluid dynamics and the rest of the portion that is left out. Till now, my other colleague Dr. Sidaram, he covered 4 chapters if I am right, module 1, module 2. I am going to touch on module 3 and module 4. Before actually start this fluid dynamics, let us have a quick recap of what you studied till now. You started with the definition of fluid mechanics. So fluid mechanics is that branch of science which deals with the behavior of fluids both at rest as well as in motion. We all know that this fluid mechanics is divided into 2 branches, fluid statics and fluid dynamics. Under this fluid dynamics, there are again 2 branches. One is called fluid kinematics, the other one is kinetics. If I don't consider the external forces that causes the motion, then the branch is called kinematics. If I consider the external forces that cause the motion, then that branch is called kinetics. When I am talking about kinematics, the one which you studied last, there we are talking about velocity, accelerations. Now the chapter which I am going to deal right now in this class and the next couple of classes, we are going to see what are the external forces that cause the motion. If I recall, you already studied 3 basic laws of fluid mechanics. One is law of conservation of mass. Mass can neither be created nor be destroyed in a system. The second one is law of conservation of energy. Energy can neither be created nor be destroyed. And finally, you have what is known as impulse momentum principle, which you are going to study in this chapter, fag end of this chapter. In addition to that, you also studied couple of definitions. One is streamline. You studied couple of other definitions. The definitions what I presented here are the definitions which I need for this class and the next class. You studied this streamline. It is an imaginary line drawn in a flowing fluid in such a way that the tangent to this line at any point gives the direction of velocity in the direction. That is what is called streamline. You also studied this stream tube. Stream tube is an imaginary tube formed by a number of streamlines. This stream tube may be circular or may not be circular. You also studied different types of flows. Among those different types, one important definition is the steady flow and unsteady flow. The various physical characteristics such as depth, velocity, density, temperature, etc. if they do not change with respect to time, the type of flow is called steady flow. If these parameters change with respect to time, then it is called unsteady flow. If I am right, all these definitions you studied till now. Now with these basics, let us start this fluid dynamics. Now the objectives of this chapter is derive Bernoulli's equation, demonstrate practical uses of the Bernoulli and continuity equation in the analysis of flow, introduce momentum equation of a fluid, then demonstrate how the momentum equation and the principle of conservation of momentum is used to predict forces induced by flowing fluids. Now another slide of this, I just elaborated what I presented earlier. Apply the mass equation. You already studied law of conservation of mass in the previous chapter. We are going to use this mass equation or law of conservation of mass in this chapter also. So apply the mass equation to balance the incoming and outgoing flow rates in a flow system. Recognize the various forms of mechanical energy, work with energy conversion efficiencies. Understand the use and limitations of the Bernoulli's equation and apply it to solve a variety of fluid flow problems. Work with the energy equation expressed in terms of Hertz and use it to determine turbine power output and pumping power requirements. These uses are, you are going to use this when you are going to talk about this hydraulic machines, that is when you are talking about centrifugal pump and different types of turbines. let me start this introduction. This chapter deals with three equations which I mentioned earlier. One is the mass equation, is an expression of conservation of mass principle. The Bernoulli equation is concerned with the conservation of kinetic energy, potential energy and flow energies of a fluid stream and their conversion to each other. The energy equation is a statement of the conservation of energy principle, and finally we have this momentum equation. Let us start with the first introduction. Now I request all of you to concentrate on the figure what I gave in the slide. If you look at this slide, so I consider a fluid mass in a flowing fluid separated by section 1 and 2 by a distance L. Now what are the various forces acting on this control volume or the fluid weight? Now one is the pressure forces at both ends, then it has a self weight, then we have what is known as the frictional force, and in addition to we have what is known as the surface tension force, then we have turbulence force, and finally we have what is known as compressibility force. Now before going to these different types of forces that are acting on the fluid element, let us see what is this fluid dynamics. At the beginning I said, when I am talking about the various forces that causes the motion, then that study of the fluid mechanics is called dynamics. The same thing I presented in this slide. Now this is the one what I told you now. One is the various forces acting on the fluid element. One is self weight, it is also called gravity force. The second one is pressure force. The third one is viscous force. Fourth one is turbulent force. Next one is surface tension force, and finally we have compressibility force. Now before proceeding further, now I request all of you to keep one thing in mind, that this fluid mechanics what you are going to study or studying right now is based on Newton's laws of motion. In other words, this fluid mechanics is also called Newtonian mechanics. Now this fluid mechanics or the dynamics of fluid is governed by Newton's second law of motion, which we all know that sigma F is equal to m into A, or which states that the resultant force on any fluid element must be equal to the product of the mass and the acceleration of the element. Now consider the left hand side. It talks about sigma F. Now just now I said on the control volume or the fluid element, what are the various forces that are acting? So I said self weight, pressure force, viscous force, turbulent force, surface tension force, compressibility force. That is what I presented in the next step. Sigma F is equal to Fg plus Fp plus Fv plus Ft plus Fs plus Fc. This must be equal to m into mass into acceleration. Now surface tension force and compressibility forces are not significant most of the times and may neglected. Now if you neglect these last two terms, that is f of s and f of c, in equation 1, the resulting equation is sigma f of f is equal to f of g plus f of p plus f of v plus f of t, that is equal to m into a. Now this equation is called Reynolds equation of motion and is used in the analysis of turbulent flows. For most of the time we talk about what is known as laminar flow. In the last chapter you studied a laminar flow, turbulent flow and transitional flow. How do you define a laminar flow? So fluid moves in the form of layer. If the fluid particle from one layer as it traverses over a distance, if it not crosses to another layer, okay, then that type of flow is called laminar flow. If I talk about a turbulent flow, in case of a turbulent flow, the fluid particles are randomly moving from one layer to another layer. Now this Reynolds number differentiates between laminar and turbulent flow. We all know that if the Reynolds number is less than or equal to 2000, we call it as a laminar flow. If the Reynolds number is more than 4000, we call it as what is known as turbulent flow. In between this 2000 and 4000, we call it as what is known as transitional flow. This is a recap of what you studied in the earlier chapter. Now If I neglect this turbulent force, then equation 1 becomes sigma F is equal to F of G plus F of P plus F of V, that must be equal to M into A. This equation is called Navier-Stokes equation. Now, in the previous equation, if I neglect this viscous forces F of V, then the equation 1 becomes sigma F is equal to F of G plus F of P, that is equal to M into A, and this equation is called Euler's equation of motion, which you are going to study in this semester. Now, this Euler's equation of motion is very, very important. Let us see how to derive this Euler's equation of motion. Okay, and from Euler's equation of motion, we need to derive what is known as Bernoulli's equation, a very important equation in fluid dynamics. Now, in order to derive this Euler's equation of motion, consider a streamline. So, at the beginning of this class, I said streamline is an imaginary line drawn through a flowing fluid in such a way that the tangent to the streamline at any point gives the velocity in the direction. So, I consider a streamline in the S direction. The yellow line what you are seeing in the figure is a streamline in the S direction. You may ask me one question, sir, why S direction, why not X direction, Y direction or Z direction? Okay. So, it is for my convenience. There is no odd and fast rule that you have to consider only in S direction. See, I presume that this streamline is in S direction. On this streamline, I consider a fluid element. Okay. So, this fluid element is having a cross sectional area dA and length ds. So, whatever you are seeing is the length of the fluid element. At both ends, you have a cross sectional area of dA. Now, remember, in case of a Euler's equation, we are considering two forces. One is the pressure force. So, pressure force, when I am talking about pressure force, we have pressure force at both ends of the fluid element, and also the self weight or the gravity force. Now, we all know that this gravity force is always acting vertically downwards. That is what I mentioned in this paragraph. Now, forces acting on the fluid element are pressure force at both ends, pressure force. Now, let us talk about the pressure force at this point. Now, we all know that this pressure force is given by pressure, intensity of pressure into the area on which it acts. Now, here I mentioned this intensity of pressure as small p and the cross sectional area as dA. Now, this intensity of pressure into dA will gives me the pressure force at this entry point of the fluid element. Now, come to the other outlet of this fluid element. Here, what is the force that is pressure force that is acting here? One is the pressure force, whatever the pressure force that is acting here, plus, so dou P by dou S, the variation of pressure with respect to S direction, because my fluid streamline is in S direction. So, the variation of pressure in S direction over what length? So, the length of the fluid element is dA. Now, remember, this portion will gives me the intensity of pressure. This intensity of pressure into the area on which it acts dA will gives me the pressure force. Remember, here the pressure force is acting in the direction of the streamline, and here the pressure force is just opposite to the initial direction. Now, at the beginning I said this gravity force is always acting vertically downwards. Usually this is the weight of the fluid element. So, this W, I replace the W as rho g dA into ds. I will tell you how I wrote this rho g dA ds in the next slide. I will come back to this slide very frequently till we derive the equation for this Euler's equation. This is what I said, the pressure force P into dou P by dou S. Again I repeat, right now I am talking about S direction. I am looking for the variation of pressure in the S direction over what length? The length of the fluid element is ds. This whole unit will gives me the pressure, and that into area on which it acts is the pressure force. Now, gravity force W acting vertically downwards. Then Remember here the angle between the streamline and this vertical line, I represent this as theta. Now let theta or pi is the angle between the direction of flow and the line of action of the weight of the element. Now according to Newton's second law of motion, I said at the beginning it is based on Newton's second law of motion, sigma f is equal to m into a. Now here I put a subscript s because my streamline is in s direction. Therefore sigma f of s is equal to ma into s. Remember, again I repeat, this s represents the direction of the streamline. Now put the various forces acting on the fluid element at the beginning, and again I am telling, when I am talking about Euler's equation, there are only two forces where we need to consider. One is the pressure force, the other one is the gravity force. Now if I take the pressure force which is acting in the direction of the streamline as positive and the force which is acting opposite to the initial direction as negative, then resolve the forces in the direction of the streamline. We have, if you put that, my sigma f of s is equal to p into dA, which is acting vertically upwards, minus p dA plus dou p by dou s into ds into dA. This is in the opposite direction at the other end of the fluid element, minus w is acting vertically downwards. When you resolve this along the streamline, so the component of this w with respect to the streamline becomes w cos theta. If you simplify this p dA and this p dA gets cancelled, you are left with sigma f of s is equal to minus dou p by dou s into ds into dA minus w cos theta. Now sigma f of s is equal to, so again remember whatever terms I am talking about is the resultant force acting on the fluid element. Now that must be equal to mass into acceleration of the fluid in the s direction. Now we will go to the next step. Now here let us talk about this w. The one what I showed here is the point right now I am concentrating. Go back to your first chapter. There you defined specific gravity, then specific weight, mass density, etc. How did you define this specific weight? Specific weight is defined as the weight divided by volume of the fluid element in general. W by V is equal to gamma. So specific weight is represented by gamma. This is what I presented here. So weight by W is equal to gamma. Now basically remember I said the vertical component I represented as W there. Now I am looking for this W. So this W is equal to volume of the fluid element into the specific weight of the fluid element. We know one more relation. What is the relation? The relation between mass density and specific weight, that is gamma is equal to rho into g. That is what I presented here. Now in this case the fluid element is very small. I am going to replace this capital V is equal to small dV. So small dV, what is the volume of the fluid element? Volume of the fluid element is equal to area into length. So dA is the cross sectional area and the length of the fluid element is ds. Therefore this dV is equal to V is equal to dA into ds. Now concentrate on this. W is equal to V into y. This V I am going to replace by dV, dV into gamma. So dV into gamma is equal to, therefore this dV is given by dA into ds and gamma is given by rho g. Therefore this weight of the fluid element is equal to rho g into dA into ds. This is what I presented in the figure. Let us have a look. Look at this. This W is given by rho g into dA into ds. I hope it is clear. Now similarly come to the next line. You define this mass density as the ratio of mass divided by volume, m divided by v. So basically I am looking for m. Why do you need that m? Because Newton's second law says that sigma f is equal to m into a. On the right hand side you have m into a. Right now you are talking about s direction, therefore ma of s. So I want to replace this m by some other term. Let us see how I am going to do that. For that, so I define this mass density. Mass density is equal to mass by volume. I am looking for m. M is equal to rho into V. Remember, in the earlier step, V I said it is very small, therefore V is replaced by dV. Again, that is the volume is given by area into the length, that is dA into ds. Therefore, m is equal to rho into dA into ds. This is what I was mentioning about. Therefore, sigma f of s is equal to minus dou p by dou s into ds dA minus w cos theta is equal to m into as. Now remember, m I am going to replace by this rho into dA into ds. If you introduce all these terms, so the equation becomes sigma f of s is equal to minus dou p by dou s into ds into dA minus rho g dA ds cos theta, that is equal to, on the right hand side you have rho dA ds into as. Now if you look at these terms, all the three terms, you have this ds dA common. So cancel this ds dA throughout. Therefore you will left with minus dou p by dou s minus rho g cos theta is equal to rho into as. Now divide throughout by rho. I repeat, divide throughout by rho, you are going to get minus dou p by dou s divided by rho is minus g cos theta is equal to as. Now come to this as. Now I want all of you to concentrate on the one what you studied in the earlier chapter, kinematics. There we know that this as or acceleration is equal to dv by dt. The variation of velocity with respect to time is nothing but acceleration, and v is a function of space and time. Now by chain rule of differentiation, I do hope that all of you studied in your engineering mathematics this chain rule of differentiation. Now this as can be written as dou v by dou s into ds by dt plus dou v by dou t. Now this ds by dt, the variation of distance divided by time is nothing but the velocity. Therefore, dou v by dou s into v plus dou v by dou t. If you simplify this, you are going to get this. Now remember, in this case, I replace this ds by dt as the velocity. That is the only thing I did. Therefore, the sigma f of s is equal to minus dou p by dou s divided by rho minus g cos theta is equal to, now on the right hand side, you in place of as write this dou v by dou s into v plus dou v by dou t. At this stage, I make an assumption. What is the assumption? The assumption is, I assume that the flow is a steady flow. So at the beginning I said the various physical parameters, if they do not change with time, then the type of flow is known as steady flow. Now if for a steady flow, okay, this dou v by dou t is equal to 0, then this equation reduces to sigma f of s is equal to minus dou p by dou s divided by rho minus g cos theta is equal to dou v by dou s into v. I hope these points are clear. Now go back to the figure what I presented earlier. There, I'll just quickly go to that. I want you to concentrate on this figure. Now this angle we represented as theta, and the vertical component I put it as dz and the inclined one as ds. So ds I said is the length of the fluid element. Okay, with reference to that, now we define this cos theta. Cos theta is equal to, so dz by ds. Now here we have this cos theta. In place of cos theta, replace the cos theta by dz by ds. If you do that, you are going to get this sigma f of s is equal to minus dou p by dou s divided by rho minus g into dz by ds minus dou v by dou s into v is equal to 0. Now since on the right hand side you have 0, and you have all negative values multiplied throughout by minus sign, automatically it will become sigma f of s is equal to dou p by dou s divided by rho plus g into dz by ds plus dou v by dou s into v is equal to 0. This equation is called Euler's equation of motion, one of the important equations in fluid dynamics. Now, let us go to this Bernoulli's equation of motion. I said this Bernoulli's equation of motion is derived from Euler's equation of motion. Now, if you observe this Euler's equation of motion, dou p by dou s divided by rho plus g into dz by ds plus dou v by dou s into v is equal to 0. Now, in Euler's equation of motion, all quantities are functions of s only. Hence, integrate this equation with respect to ds, we have, so integration of dou p by dou s divided by rho plus g into dz by ds plus dou v by dou s into v is equal to 0. Okay. Now, if you simplify this or integrate the equation with respect to ds, you are going to get this p by rho plus gz plus v square by 2 is equal to constant. Now, what I am going to do is I divide this equation throughout by g. If you divide this equation throughout by g, you are going to get this p divided by rho g plus, so gg gets cancelled, you are left with z plus v square by 2g, this is equal to constant. Now, this equation is called Bernoulli's equation. I repeat once again, p by rho g plus z plus v square by 2g is equal to constant. Now, we know the relation between the specific weight and the mass density. So, gamma is equal to rho into g. Now, if I replace this rho g as gamma, then this equation takes up the form p by gamma plus v square by 2g plus z, so is equal to constant, another form of Bernoulli's equation. Now, this p by gamma is called the pressure energy per unit weight of fluid. Now, v square by 2g is called the kinetic energy per unit weight of the fluid, and z is called the datum energy or the potential energy per unit weight of the fluid. Let us see the definition of what is potential energy, what is pressure energy, what is kinetic energy. Now, potential energy or the datum energy, remember this is represented as capital Z, is the energy possessed by the fluid by virtue of its position, very important, or location in space. Okay. Now, next one, pressure energy. It is the energy possessed by a fluid by virtue of the pressure at which it is maintained. Finally, we have this kinetic energy, v square by 2g. V square by 2g is the energy possessed by a fluid by virtue of its motion. Now, let us define the Bernoulli's equation. Now, the statement is, in a steady incompressible fluid, the total energy remains same along a streamline throughout the reach. I repeat once again, in a steady incompressible fluid, the total energy remains same along a streamline throughout the reach. Now, purposely I put this along the streamline in red, because now most of the time, so if we talk about a unsteady flow, okay, this total energy will not be constant all along the entire depth of the flow. So, that is why proper definition of this Bernoulli's equation or statement is, in a steady incompressible fluid, the total energy remains same along a streamline. Perfect definition of a Bernoulli's equation throughout the reach. Now, here I showed couple of streamlines represented by psi 1, psi 2, psi 3. Now, again I repeat, if it is a steady flow, the Bernoulli's equation or the total energy remains same all in the three streamlines. Suppose if it is not a steady flow, then the total energy at psi 1, total energy at psi 2, total energy at psi 3 are different. Let me take you to the first chapter where you studied two types of fluids. One is a ideal fluid, the other one is a real fluid. So we defined ideal fluid as fluid which do not possess viscosity, there is no surface tension, and ideal fluids cannot be compressed to a great extent. This is how we define a ideal fluid. A real fluid is one which possesses surface tension, they possess viscosity, and they can be compressed to some extent. This is the difference between ideal fluid and a real fluid. When I am talking about a ideal fluid, how my total energy or the Bernoulli's equation look like so in a real situation. So in order to give the Bernoulli's equation for a ideal fluid flowing in a pipe, I consider a pipeline. On this pipeline I introduce two piezometers separated by a distance L. Now what you are seeing here is this is one piezometer, this is another piezometer. Remember, when I am talking about an ideal fluid, I am not talking about any losses. Now just now I said this Bernoulli's equation or the total energy consists of datum energy, pressure energy plus kinetic energy. Since when I am talking about a ideal fluid, there are no losses, whatever the total energy you are observing at section 1, the same amount of total energy you are going to see at section 2. So in this case my Bernoulli's equation is of the form, so P1 by gamma plus V1 square by 2G plus Z1, that is P1 is the intensity of pressure at 1 and V1 is the velocity at 1 and Z1 is the datum height or the potential energy at 1. Similarly at section 2, so P2 by gamma plus V2 square by 2G plus Z2. Now this must be equal to constant. In other words, when I am considering a ideal fluid, from the starting point to the end of the flow, the total energy remains at any section. So this is in case of a ideal fluid. But in nature, most of the time we encounter real fluids. Now if there is a real fluid flowing in a pipeline, how my Bernoulli's equation look like? That's very, very important. So from practical point of view, let us see how it look like. Now in case of a real fluid, remember when I am talking about a real fluid, I said the fluid possesses viscosity, it has surface tension, so these fluids can be compressed to some extent. In other words, when I am talking about a real fluid, there are always losses. So whenever there is a flow, so the flow or the surface in which the fluid is in contact with, it offers some resistance. In other words, there is always a flow drop or pressure drop from section 1 to section 2. That's what I presented here. Again, I consider a pipe carrying a real fluid. On this pipeline, I consider two piezometers, piezometer 1 and piezometer 2. Again, these two piezometers are separated by a distance L. Now, at section 1, the total energy is given by Z1 plus P1 by gamma plus V1 square by 2G. Now, when you come to the section 2, okay, just now I said there is a pressure drop or energy loss from section 1 to section 2. If you look at this pipe is horizontal pipe Z2 and here the pressure energy is given by P2 by gamma and the kinetic energy is given by V2 square by 2G. Now in the earlier case I said there is no pressure drop. We have, so whatever the total energy you are observing at piezometer 1, the same total energy you are observing at total piezometer 2. So in this case, since we have a pressure drop or a pressure loss, now this pressure loss we expressed as what is known as head loss. Now remember, whatever the total energy you are encountering at this, that must be equal to the total energy at this. That is what the Bernoulli's equation states. Now in this case, the Bernoulli's equation becomes the total energy is equal to P1 by gamma plus V1 square by 2G plus Z1, that must be equal to P2 by gamma plus V2 square by 2G plus Z2 plus, never ever forget this, because if you don't this component, then this height from the datum is not equal to this height. Remember, the total energy remains the same all along the flow, that is what Bernoulli's equation states. If at all if you want to equate the total energy at this point and this point, then don't forget to add this HL. That's what I did here. So P2 by gamma plus V2 square by 2G plus Z2 plus HL, this must be equal to constant. Okay. Again I repeat, whenever I am talking about a ideal fluid, there are no losses. Okay. This HL term becomes 0. Whenever you are talking about a real fluid, there will be a loss, head loss, and this HL is called head loss. I hope these points are very clear. Now coming to the limitations on the use of Bernoulli's equation. Now remember, while deriving that equation, I made an assumption, or in fact we made an assumption. What is that assumption? We assumed that the flow is steady. But you studied in your earlier chapter, most of the flows that are available in nature are unsteady flows. Okay, it is very difficult to find a steady flow in nature. All the flows that are available in nature are unsteady flow. If that is the case, the first limitation of the Bernoulli's equation is that it is applicable to steady flow. Then second one is, I said whenever I am talking about a real fluid, there are most of the time there will always be a loss. Now in this case, so if you recall the figure what I showed in my first slide, I didn't mention about the frictional force. Okay. So here we neglected that frictional force, that is another important limitation of this Bernoulli's equation. Then the third one is incompressible flow. One of the assumptions used in the derivation of Bernoulli's equation is that so mass density is constant and the flow is incompressible. But in a real situation, this will not be the case. Okay. Now strictly speaking, Bernoulli's equation is applicable along a streamline. This is what I mentioned earlier. The value of the constant C in general is different for different streamlines. Recall, I put 3 streamlines, psi 1, psi 2, psi 3. But when a region of the flow is irrotational, okay, so you recall you studied what is known as rotational flow and irrotational flow. If the fluid particles do not rotate about their mass centers in the direction of flow, it is called irrotational. If the fluid particles rotate about their mass centers in the direction of flow, it is called what is known as rotational flow. Now when a region of the flow is irrotational and thus there is no vorticity in the fluid flow field, the value of the constant remains same for all the streamlines, and therefore the Bernoulli's equation becomes applicable across streamlines as well. So on this assumption, if you take out any textbook, most of the time they will never say that this Bernoulli's equation holds good for a streamline. They say that so between section 1 and section 2 the total energy remains same. But again I repeat, if you talk about a turbulent flow, okay, so it varies from streamline to streamline. That is another limitation. Now we talk about what is known as kinetic energy correction factor. For the first time I am introducing, I do hope my colleague mentioned this variation of velocity with respect to depth of flow. Now the first figure what you are seeing here, okay, so here this is the free surface and this is the depth of the base of the, or what you call it as the bottom of the channel or the pipe. If you take the velocity profile is look like this. Remember, at the bottom of the pipe or at the channel, velocity is almost 0. At the same time, at the free surface, the velocity is not maximum, sorry. Now velocity is maximum at certain depth. Okay, this is a typical velocity profile. Okay, now that is what I presented in this figure. The pink one what you are seeing is the actual profile of velocity versus the depth. But in deriving the Bernoulli's equation, we made an assumption that this velocity is average from the free surface to the depth. Okay, I repeat, so this is the actual profile of velocity, but while deriving the Bernoulli's equation, we presume that there is average velocity from the free surface up to the bottom of the pipe or the channel. That is what I mentioned in this paragraph. In deriving the Bernoulli's equation, the velocity head or the kinetic energy per unit weight of the fluid has been computed based on the assumption that the velocity is uniform over the entire cross section of the stream tube. Okay, but in real fluids the velocity distribution is not uniform. Therefore, to obtain the kinetic energy possessed by the fluid at different sections is obtained by integrating the kinetic energies possessed by different fluid particles. Again I repeat, the actual velocity profile is like this. Now in deriving this Bernoulli's equation, we assume that the velocity is average from the free surface up to the bottom of the pipe or the channel. It is more convenient to express the kinetic energy in terms of mean velocity of flow. I repeat, it is more convenient to express the kinetic energy in terms of mean velocity of flow. But what is the disadvantage? The disadvantage is, but the actual kinetic energy is greater than the computed using the mean velocity. If I apply mean velocity, the actual kinetic energy is greater than what is computed. Hence, a correction factor, again I repeat, hence a correction factor called kinetic energy correction factor, which is represented as alpha, is introduced. Again I repeat, kinetic energy correction factor, why alpha is necessary? Alpha is necessary because when we are deriving the Bernoulli's equation, we presume that the velocity is average from free surface up to the depth or the bottom, but the actual velocity profile is not average from the free surface up to the bottom. So for this, it is more convenient to express the kinetic energy in terms of mean velocity of flow. But if I consider this mean velocity of flow, the actual kinetic energy is greater than the computed. So hence this correction factor is necessary. That's why this kinetic energy factor represented by alpha is introduced. Now, if I introduce the kinetic energy factor in the Bernoulli's equation, then the Bernoulli's equation becomes the total energy is given by P1 by gamma plus V alpha 1. Alpha 1 is the correction factor for this kinetic energy. So V1 square by 2G. Remember, and you must be very careful, I am applying this kinetic energy correction factor only to this kinetic energy, not the pressure energy and the datum energy, plus Z1. This must be equal to P2 by gamma plus again alpha 2 at section 2 V square by 2G plus Z2 plus HL. Remember, here I presume that the fluid is a real fluid. Again I repeat, if it is an ideal fluid, HL is 0. This must be equal to constant. This is very important. This will be of great help for you when you are solving the problems. In most of the problems of turbulent flow, the value of alpha is equal to 1. Now if you put this is equal to 1, then this equation again boils down to T is equal to P1 by rho gamma, sorry, there is a correction here, kindly correct this. This is P1 by gamma plus alpha 1 into V1 square by 2G plus Z1, that must be equal to P2 by gamma plus alpha 2 into V square by 2G plus Z2. Okay. Now, the general equation is, okay, so this is a perfect equation. Now, if you assume that alpha is equal to 1, this equation boils down to, so this is equal to 1 and this is equal to 1, you have this P1 by gamma plus V1 square by 2G plus Z1, that must be equal to P2 by gamma plus V2 square by 2G plus Z2. Again I repeat, I am sorry, kindly replace this rho by gamma. That's about Bernoulli's equation. Let us solve simple 1 or 2 problems, then we will see the applications of Bernoulli's equation, then we will start solving these complicated problems. So to begin with, to give a flavor of the combination of this law of conservation of mass and law of conservation of energy, let us start with a simple problem. The problem is like this: a converging pipe 30 centimeter and 15 centimeter diameter carrying water is positioned inclined, whose inlet and outlet are at 6 meter and 1 meter above the datum. The pressure at inlet is 1.5 bar and velocity is 5 meter per second. Find the pressure of water at the outlet of the pipe neglecting the losses. I repeat, in order to solve this problem, we are going to make use of law of conservation of mass and law of conservation of energy. Let me repeat, law of conservation of mass states that mass can neither be created nor be destroyed. That is, Q1 is equal to Q2. If you recall, so whatever the amount of discharge that enters here, the same amount of discharge is flowing out from this. So, in this case, we know this Q is equal to A into V, and if I apply that here, Q1 is equal to A1 V1, and here Q2, which is nothing but Q1, in general Q is equal to A2 into V2. So, in general, this Q is equal to A1 V1 is equal to A2 V2. That is law of conservation of mass. I am going to apply this equation in order to solve this problem. First, let us see what is the data that is given in the problem. Now, we know this value of Z1. Z1 is 6 meters given in the problem. Now, the diameter at inlet is 0.3 meter. The velocity at inlet is 5 meter per second, and P1 is equal to 1.5 bar. So, in the first chapter, so you already studied this units of pressure. Sorry. So, 1.5 bar. Now, 1 bar is equal to 1 into 10 power 5 Newton per meter square. 1 Newton per meter square is called Pascal. So, therefore, P1 is equal to 1.5 into 10 power 5 Pascal or Newton per meter square. This is the given data. Now, let us see with this data how to solve this problem. Look at the first step. Applying continuity equation between 1 and 2, we have. So, Q1 is equal to Q2 is equal to Q. I said whatever the amount of discharge that enters the inlet, the same amount of discharge must come out of the suction according to law of conservation of mass. Now, Q1 is equal to A1 V1 is equal to A2 V2. Now, you make use of this relation. At inlet section, now A1 is equal to pi d square by 4, 3.14, the dia at inlet is 0.3. So, pi d square divided by 4, the area at inlet is given by 0.071 meter square. Now, velocity at inlet is 5 meter per second, that is given. Now, at outlet section, area A2 is given by again pi d2 square by 4. Now, if you work out that, you are going to get this as 0.018 meter square. Now, consider this equation A1 V1 is equal to A2 V2. You have A1, you have V1. Just now you calculated the value of A2. What is the unknown? Unknown is V2. So, therefore, V2 is equal to A1 V1 divided by A2. You know all these values, substitute the values and find the value of V2. If you find the value of V2, V2 works out to be 19.625 meter per second. Now, with this, now we will apply Bernoulli's equation between section 1 and 2. Now, what is Bernoulli's equation? Now, Bernoulli's equation presume that it is a real fluid, but in this case HL is 0, therefore, it is a ideal fluid. P1 by gamma plus V1 square by 2G plus Z1, this must be equal to P2 by gamma plus V2 square by 2G plus Z2 plus HL. Now, P1 is given in the problem 1.5 into 10 power 5 and gamma is for water, it is 9810 Newton per meter cube, and V1 square, just now V1 is given in the problem 5. So, 5 square divided by 2 into 9.81 and Z1 is 6, that is given in the problem. So, P2 is unknown value divided by 9810 plus, just now you calculated the value of V2 19.625, divided by 2 into 9.81 plus Z2 is 1. In the given problem, my HL value of HL is 0, therefore, I put this HL is equal to 0. If you simplify this, you are going to get the value of P2 is equal to 0.118 bar. It is a very simple problem. So, to give a flavor of the combination of this law of conservation of mass and law of conservation of energy. Now, we will go to the next problem. I'll make it little complicated. So, here it goes like this. Water flows through an inclined pipe of 2 meter long, having a slope of 1 in 20. The pipe tapers from 5 meter diameter to 1 meter diameter from higher end to lower end. Water flow is 500 liter per second. The pressure of water at the entry is 1.2 bar. Find the pressure of water at the exit. Remember, if you recall the earlier problem, in the earlier problem, you know the value of Z1, you know the value of Z2. So in this case, you don't know the value of Z1 and Z2, but you know what is the angle made by this inclined pipe with respect to this horizontal. That is what is given in the problem. So it is having a slope of 1 in 20. Okay. Now let us see again what is the given data. Given data is tan alpha is 1 by 20. At the inlet the diameter is 5 meter. At the outlet diameter is 2 meter. The discharge flowing in the pipe is 0.5 meter cube per second, and at the inlet the intensity of pressure is 1.2 bar. Again I said 1 bar is 1 into 10 power 5 Newton per meter square, or 1 into 10 power 5 Pascal. So therefore P1 is equal to 1.2 into 10 power 5 Pascal or Newton per meter square. The length between, remember this is the inclined length from A to B, is 50 meter. Okay. Again we will do the same procedure what we followed for the earlier problem. Okay. So apply continuity equation between 1 and 2. So we have this Q is equal to Q1 is equal to Q2. So this Q1 is given by A1 V1, Q2 is given by A2 V2. Therefore this A1 V1 is equal to A2 V2. Remember, in the given data we know the discharge flowing in the pipe. Discharge flowing in the pipe is 5 meter cube per second. Okay. So therefore A1 is, so pi d square divided by 4. At the inlet the diameter of the pipe is 5, therefore it is pi into d square, 5 square divided by 4, that into V1, and when you come to the right hand side it will be pi d square d2 square into V2, that is 3.14. At the outlet the diameter is 1, therefore it is 3.1 into 1 square divided by 4 into V2. Therefore V1 is equal to, so 20 divided by 3.14 into 25, or if you simplify this you are going to get this V1 is equal to 0.27 meter per second and V2 is equal to 6.7 meter per second. Now tan alpha is 1 by 20. If you find the value of alpha, alpha works out to be 2.86. Now basically I am looking for sin alpha. Okay. So this sin alpha is equal to Z1 minus Z2 divided by length. Okay. Now this sin 2.86 is equal to Z1 minus Z2 divided by the inclined line that is given in the problem is 50. Therefore you know all the values except the difference between the two elevations Z1 and Z2. Therefore this Z1 minus Z2 works out to be 2.5 meter. Now with this data, let us apply Bernoulli's equation between section 1 and section 2. Now again at section 1, P1 by gamma plus V1 square by 2G plus Z1, that must be equal to P2 by gamma plus V2 square by 2G plus Z2 plus HL. In this case also the value of HL given is 0, therefore I put this HL is equal to 0 in this case. Okay. Now what is your aim? Your aim is to find the value of P2. So therefore take this term to the left hand side and push all of the terms to the right hand side, and if you push all of the terms to the right hand side and if you substitute the values, whatever the values you calculated above, and if you work out this value of P2, P2 works out to be 1.22 bar. Okay. So these two problems give the relation between this law of conservation of mass and law of conservation of energy.